Welcome back. This is our last section for this unit, and we'll be looking at acceleration due to gravity near Earth's surface. This is a pretty large topic, so this will just be our intro to the concept, and we'll pick it up in future lessons, both in this course and in grade 12. So all objects with mass experience an attractive force that is referred to as gravity. It's what holds you on this Earth. The sun's gravitational pull is what keeps the planets in their orbit. The Earth's gravitational pull is what causes objects to fall to the ground when they're not supported. The gravitational pull or force on Earth causes objects to fall with an acceleration of 9.8 meters per second squared. And we're going to spend some time talking about that. Or 32.2 feet per second squared, but we'll only be working with the 9.8. As we will learn in our next unit, the force of gravity is dependent on how close the two objects are together. Okay, so gravitational force can vary somewhat around the globe. The symbol for the acceleration due to gravity is g. Big surprise. And the direction of the acceleration is always towards the Earth and is usually represented with a negative sign to communicate down. So this is typically what we will always be using for our g value, negative 9.8 meters per second squared. Okay, so let's get right into it. We have our 5 kinematic equations listed to the side. We'll do the same approach we've done in the past section. So a flower pot is knocked off a window ledge and accelerates uniformly to the ground. If the window ledge is 10 meters above the ground and there's no air resistance, how long does it take the flower pot to reach the ground? Okay, so let's try and get a few things down here. What is given? Well, it said it was on a ledge, so we can assume it starts at 0 meters per second. It is 10 meters off the ground, and we're going to come back and talk more about that value in a minute. It accelerates uniformly, so that's downward at negative 9.8 meters per second squared. And then we're looking for time. How long does it take? So we're trying to find a time value. So what equations might be useful for this one? So we're trying to find time. We have VI, D, and A. Okay, so we don't need equation 2. We're not looking for final velocity yet. We are equation 3. We have a lot of those pieces, but it could get a little bit messy. But we're going to try it anyways. Let's go for equation 3. So we're going to have D equals VIT plus 1/2 AT squared. Okay, now where this gets messy, if we had an initial velocity that was not 0, then this would become a quadratic problem. But because we have an initial velocity that's 0, this first term is going to disappear and go to 0, because 0 times t will be 0. So if we had initial velocity, it gets a little trickier, but because it's 0, this problem simplifies to be quite nice. So our d, I'm going to put a 10 in here, and then I'm going to put 1/2 negative 9.8 t squared. I'll just drop my pen for a second. There we go. And now we're going to do a couple calculations. Divide both sides by negative 4.9. Those cancel. And we're left with 10 over negative 4.9. And to undo a squared term, we are going to square root both sides. And here we encounter our first problem. Okay, so if you try this on your calculator, and I encourage you to try it, go 10 divided by negative 4.9, hit your equal sign, and then try and take the square root of that answer, and you will get an error. Okay, and the error is because this 10 value up here, we are starting on a ledge and we are descending downward. So that is a negative displacement, because for this question we have negative meaning down. We use that for our acceleration. So the next part that we're going to add to these problems is we want to put our sign convention. So positive will be up. If something moves downward, it's going to get a negative sign for the direction. So we will change this 10 here to be a negative 10. Okay, so that was an intentional error on my part, because I want to show you that you can't just hammer through with the calculator. So now if we make that 10 negative, Now we can go through and try 10 divided by 4.9. Then two negatives cancel each other out. Then we take the square root of that answer, and we should get 1.4. Okay, and that would be, oh, get out of there, 1.43 seconds would be our time value to fall 10 meters to the ground. Okay, so things to watch. The direction's important. Okay, we're going to start using this sign convention. So we'll list which way we are assuming is to be positive, and we might want to start introducing little pictures. They make a big difference. Okay, so what if the final velocity of the flower, what is the final velocity of the flower pot just before it hits the ground? So let's draw our picture. We had a flower pot sitting on a ledge. It has fallen off the ledge, and we want to know right before it hits the ground, okay, what is the final velocity? Okay, so let's list what we know. We have v initial is 0, acceleration's negative 9.8 meters per second squared, d is negative 10 meters, and I'm going to put this in a slightly different color. We actually know the time. It's 1.4 seconds. But I'm going to try and avoid using that. And the reason I want to avoid using the time value, if I can, is because it's a calculated value. And if I say I've made a mistake in that, I've rounded it off too much, I'm going to be compounding those mistakes in the rest of my question. So what I would like to try and do, if possible, is solve this problem without using a calculated value. I want to see if there's enough information that was given outright. So if we look at, we have VI, A, D, and VF. So I'm looking at equation 4, and I'm thinking that will be a good place to start. So if we start with VF squared equals VI squared plus 2AD. We're looking for VF. VI is 0. 2 is a constant. A is negative 9.8 and D is negative 10, so we're keeping track of those negative signs, very important. VF squared equals, I think that's 196, better check, let's see, 10 times 8 times 2, 196, very nice. And it's positive, so that's going to make my square rooting a lot simpler. We square root both sides, and we get VF equals 14 meters per second down, or we could write it at negative 14 meters per second. And you could say, well, why are you just sticking that answer in there? I'm not. Just a reminder that the square root, let's go over here. If I take the square root of 4, the answers are 2 or negative 2, because if you multiply 2 times 2, you get 4. If you multiply negative 2 times negative 2, you get 4. So there are actually 2 answers to this one. So it could be positive or negative 14, so we're actually looking for the negative 14. Okay. Pause it here. You can try these ones. I'll try and go really quick. We'll see how we do for time. So pause it here and then try these, please. Okay, so in the interest of time, I'm not going to do the entire questions. A ball is dropped from the roof of a building. It takes 2.6 seconds to reach the ground. How tall is the building? So we're looking for D. We have a VI of 0. We don't need VF. We have a given T value of 2.6 seconds. And we have an acceleration of negative 9.8 meters per second squared. So I need an equation that ties those together. And I'm going to use the third equation, which is a pretty popular equation. So D equals 0 plus 1/2 negative 9.8 2.6 squared. And all of that is just a big calculator problem. So 9.8 times 2.6 times 2.6 times 0.5, 33 meters, and we'll say it's negative because it's down, and there's our 33. So if we wanted to, we could also put down. Okay, A hot air balloon is hovering a distance above 52 meters above the ground. Hot air balloon. I'm not going to solve this one. I'll just reveal the answers, but let's make sure our setup is correct. 52 meters. A penny is dropped from the balloon, so we have an assumption that VI is 0. We know acceleration is negative 9.8 meters per second squared. How long does it take the penny to hit the ground? Okay, so this is D, and again, we could make that negative 52. So the first one, we've done this one already once or twice. It's the same as the flower pot, so we should get a time value of 3.3 seconds. Okay, and what is the final velocity of the penny? Again, just like the flower pot question, only this time it's going to be 32 meters per second. Okay, so I hope those worked. If not, we'll try some more. Okay, determining the height reached by a ball thrown straight up in the air. So we're going to adventure into something called projectile motion in our next unit. This is the first place we're going to get the groundwork started. So if a tennis ball is thrown straight up in the air, remember we're doing one-dimensional motion, so there won't be any moving left or right. It's just going to go straight up in the air. Okay, with an initial velocity of 6 meters per second. So I'm going to say VI is 6 meters per second. Acceleration is negative 9.8 meters per second squared. So we are asked, how high from where it was thrown does the ball go? So that is what we're trying to find out. Now there's one piece of information here that is not written and that you will be responsible to know and remember. And that is at the very apex, the very peak, right over here, at that highest point, the ball actually stops. Okay, so on its journey upward, on its highest point, VF is 0. And this is at the top. And I like to put in the little brackets to describe where these things are happening, because sometimes it can get very confusing. So those are our pieces of information to do the journey from the hand to the top. Okay, and that will allow us to figure out what D is. So if we look at our equation, I'm thinking equation number 4. VF squared VI squared plus 2AD. Put in our known information, 0, 6 squared, 2, negative 9.8, and a D. Okay, and I'm going to shortcut a few lines here just in the interest of time and speed. So 0 equals 36 minus 19.6D. 19.6D, if we add that to both sides, and then we divide both sides by 19.6. Again, if you have to pause it and go through the math slower, that's totally fine. I'm just trying not to make the video too long. Looks like 1.84, we'll say, meters. Let's just go 1.8. 1.8 meters. It's positive value, so we know that is up. So that's how high the ball ends up, almost 2 meters, not quite above the person's hand before they smash it with the racket. Okay, so have a look. The main piece here is this one. You have to know that the apex, that piece will be 0. Okay, so another one. Practice. You could pause this and then try it. It's very similar to the tennis question, but it has a few more parts. All right, so let's try it. A golf ball thrown straight up in the air at a velocity of 8.3 meters per second. So we have our givens. We have acceleration. Okay, so first question, determine the maximum height. Okay, so VF is 0 at the top. So we are looking for our max height, which is what we're trying to find. So again, I'm going to go back to equation 4. And we'll make some substitutions. So 0, 9, oops, not 9.8, 8.3 squared plus 2, negative 9.8, and D. Okay, so 8.3 times 8.3. So that is 68.9 minus 19.6D. Rearrange. And if I make a small math mistake or a large math mistake, please don't laugh. I'm trying to go quickly here under the pressure of filming, so that's always a fun little 3.5 meters. So there's the maximum height. So that is, here's the ground. This is our zero reference point. The ball has gone up. It's 3.5 meters in the air. Okay, so there's first one done. How long will it take the ball to reach its maximum height? So now we're looking for t. Okay, so we can use some of that information we were given at the start. Again, I might try to avoid, if I can, I want to avoid using the calculated values. I sometimes won't be able to, but I'm going to try. So I'm looking at VF equals VI plus AT as my equation to use. I think it's number 2. Don't remember off the top of my head. So then we can jump in at the top. It's 0. At the start it was 8.3 minus 9.8t. Rearrange and solve for t. And t, if I divide both sides by 9.8, 0. I'm going to carry 2 decimal places just for this one. So it takes less than a second to get to its maximum height. Okay, so let's go up here. There's 0.85. So we're 2 for 2. And then lastly, how long will it take the ball to fall from its maximum height to the height from which it was initially launched? Okay, so now this is a real interesting question because this leads into a whole bunch of fun thinking. If we looked at this, and I'll try and do it relatively quickly. The ball started on the ground and went up. And now we are looking at this case. The ball is in the air and falling back down. So if we list those known pieces of information, the initial velocity, if we consider the ball starting at the top, is 0. We don't know the final at this point in time. We do know the distance it has to fall is negative 3.5 meters. We do know the acceleration is negative 9.8 meters per second squared. And we are looking for time. Okay, and then maybe in the next question we'll find the final velocity. You'll see there's some interesting little patterns here. So if I want to find the time for it to fall back down to the ground, again, I'm looking at d equals VIT plus 1/2 AT squared. And again, because the VI is 0, because the ball stops at the very top, and we know this is negative 3.5 meters, we have 1/2, we have negative 9.8, and we'll work this backwards. Going to run out of room here, my apologies. Jumping around the page, trying to fit too much on here, I apologize for that. Divide both sides by negative 4.9. Those cancel. And then take the square root of both sides. And I have 2 negatives on the left-hand side, so that's good news, because they'll cancel each other out. And then I can take the square root, and again, pause it, go through the math. 0.85 seconds is the time to fall to the ground. Now, the really observant will be like, hey, that's the exact same time it took to go up. Okay, and this is not a coincidence because we're neglecting air resistance, and because we are starting and finishing at the same height, there is some repetition or symmetry to this problem. So the flight time to go up is the same as the flight time to fall. And I'll leave this for you, but we will prove it in a question or two. It won't take much to figure out that the final velocity on the way back down is the same as the final velocity that it started with going up. Okay, so this is the summary, and you can explore this in the questions you do in the future. There are 3 cases, and again, we're only doing one-dimensional motion. So case 1, if an object starts and stops at the same height, we will find that the time up and the time down is exactly the same. We will also find that the v initial and the v final at that location will end up being the same values. I'm going to let you explore that in a question though. Case 2, object starts at one height and finishes below the original height. So that means if it takes 2 seconds to get to the top here, and it's falling past where it started, it should take more time. So it'll take, I'm just guessing, say 2.4 seconds to fall past. Okay, and that value is totally dependent on where it stops. And then the last case, the object starts at one height and finishes above the original height. So if it took 2 seconds to get to the very top and then only fell partway back down, it might only take, say, a second. So it would have less time to drop. Okay, so this right here is the most symmetrical case. It's where you can use some shortcuts. The other two, there are no shortcuts. We have to chop the problem up into two flight paths. The path going from the ground to the top, and then the second path going from the top back down to the ground. Okay, so on page 43, numbers 2 through 5, if you could give those a try, that would be awesome. Thanks for tuning in.